welcome to T103 Basic Theory. So this week we're looking at floating point arithmetic operations. So we're going to be looking at some of the errors that can be caused in floating point operations. So in floating point arithmetic operations, when addition or subtraction is performed on a number with a large absolute value, so let's highlight these because we're going to have one value with a large absolute value and a number with a small absolute value, and we're going to be performing the operations on these two and seeing what if there's any issues when both aren't large or both aren't small, and we'll come on to what this means in just a minute. Which of the following refers to the phenomenon where some or all of the valid digits of the number with the small absolute value does not appear in the result? Okay, so let's have a quick look over floating points and why we use them. They're very similar to scientific form and scientific notation for numbers. So let's just quickly write a number 1, 2, 3, 4 times 10 to the minus 4. And so what we've got here is we've got a few parts of this number. We've got this part, and this part. And let's just quickly go into what these are. So this is the significand, and what this is it's all the significant figures that you need to express your number. Here we have the base. So what we use the base for is to move our decimal place up and down, so hence the name floating, so we can move the decimal place up and down our number with respect to the significant figures. And here we have the exponent, and what the exponent does is tells us how many decimal places, if we use a times 10 base, how many decimal places we're going to move along our significant figure. And so what we can see is this is actually equal to 0.1234. So as we said, it's similar to scientific form. So what it means is we can express with a relatively small number of bits, very large numbers and very small values at the same time. So let's just take two examples here, and have c, which is the speed of light, which is equal to 3 times 10 to the 8. And we've also got, let's say, the radius of a hydrogen atom. Well, that's going to be 2.5 times 10 to the minus 11. So let's just quickly have a look here, and what we can see is we know how to express 3. It's possible to also express 2.5 or 25 depending on how it's going to be used, and it's also possible to express the 8 and the minus 11 with a relatively small number of bits. So here we're able to express something that's almost 20 powers of 10 larger than another number with a small number of bits. So here we're looking at some of the errors caused in floating point numbers and looking at which of these describes the phenomenon mentioned on the previous slide. So in the addition and subtraction of floating point numbers, before the operation occurs, the values of the exponents of the two numbers are adjusted. So the exponents are adjusted basically. So the exponent was that times 10 to the power of minus 4, say, and that minus 4 was the exponent. It's the scaling of the decimal place with respect to the significant figures. In other words, the value of the exponent of the number with the smaller value is adjusted to the value of the exponent with the larger value. So we're moving the small number to be on the same scale as the larger value. And the fraction part of the smaller value becomes 0, which is the cause of the phenomenon. So this is the phenomenon we're describing, and this is the cause of it. In the addition and subtraction of multiple values, in order to prevent loss of trailing digits, so we've been describing the loss of trailing digits here. This is a method of prevention of it. So let's highlight this in a different color just so we can see that this is a prevention. Addition and subtraction is performed after the values are arranged. So after the values are arranged in order of absolute value, from smallest to largest. By doing this, the operation affects only the absolute values that have small difference, and the loss of trailing digits is unlikely to occur. So let's look, and the answer is going to be the loss of trailing digits is the phenomenon that we were looking at on the previous slide, and that's going to be the answer to the question that we had on the first slide. However, we did mention there are some methods of preventing or reducing this phenomenon. It's still going to be the answer to our question. So let's just look at some of the other errors that we've got in floating point arithmetic operations. So truncation error is an error that occurs in an operation such as in an engineering calculation, where an infinite fraction is cut off to become a finite fraction. So for example, this is our value for the speed of light, and here in meters per second, or this in standard form. which is truncated to this 2.99 times 10 to the 8, or even approximated, as I did on the first slide, to 3 times 10 to the 8. So here, what we've got is a truncation error. And basically all you've done is you've got rid of some of the significant figures. And often this isn't an issue, depending on the accuracy of the value you want. If you're looking at something that you need this amount of significant figures for, this will become an issue if you round to this. The next thing we should consider is the cancellation of significant digits. This is a phenomenon where the number of valid digits decreases due to the normalization of the fraction when two numeric values with the same sign bit and almost the same absolute value are added or subtracted. So let's look at an example on the next slide, just so we can demonstrate this phenomenon, because the words are quite hard to understand here. So let's look at this cancellation of the significant figures that we had mentioned in words on the previous slides, and let's look at this in numbers so you kind of get a better feel for it. So we'll consider these two numbers, 0.123456789, 123456789, and just 0.123456789. So the first number is accurate to 10 to the minus 20. So the exponent that we have here is minus 20, while the second is only accurate to minus 10. So this shows how accurate our number is. This one we have 20 decimal places of accuracy. This one we only have 10. So now performing the calculation of subtraction on these two, here, this first number take away this second number, the answer accurate to 20 significant figures. So if we take into account that this can be extended with zeros and assume that this is the correct value to 20 significant figures, this is going to be our output. However, on the 10-digit floating point machine, we can only consider the first 10 digits, as it kind of alludes to with this 10-digit floating point machine. So the calculation actually gives us this output here, 0.0000000001. In the second case, the answer seems to have one significant digit, which would amount to a massive loss of significance of almost 10 bits. So what we can see is that we've literally got rid of all of these numbers because we are using a 10-digit floating point machine. So this is how this error arises. The final error that we need to consider is the absolute error. This isn't actually a phenomenon of error, it's how we can measure the value of the error. So here that's just explained. Absolute error is the actual value of error. So the difference between the measured or the inferred quantity x0, and we're going to compare that with its actual value in x, and this is called the absolute error, delta x. So we can see that that's given down here. Delta x is equal to x0 minus x. So this is a measure of how accurate our equation is. So here we've seen, and our answer is B.